I'm going to continue some of that theme in what I wanted to talk about. So when Neil asked me to talk, he said give an overview of surveys. My first reaction was everyone in this room knows everything about the surveys I'm going to talk about. Half of them designed half the surveys in this room, so some version of this. So what I want to do is, what I thought I'd do was sort of ask a bunch of questions. Hopefully some of them will be stupid enough questions that will provoke all of you into saying things and yelling at me and getting some discussion started. But I also will try to give you a little bit of background and flavor of where I think some of the questions are going to come. So I think this is where I think, as if I think about the surveys, what I think we will have in the next decade, which will be a biased density map of the universe from redshift 0 to 2.5. We will be able to tell you what the large-scale structure traced by some biased tracer would look like over a very, very broad range of surveys. And I think the question from the survey point of view, and certainly when we write proposals, is what can I do with this? And we certainly write down the standard things. I'll go after dark energy. I will go after modified gravity. I'll go after neutrino masses. But what are the other things that we can do and hope to learn from all of these pieces out here? So that's where I'm going to try to at least point towards, or at least ask some of the questions. I couldn't help myself and sort of put a quick plug on some of the results, which I think sort of drive why we're having this discussion. Is surveys have been incredibly successful. And so I wanted to show you sort of the latest results from BOSS here, which just showed up yesterday on the archive. And this sort of gives you a sense of the sort of successes we've been having with BOSS. These are the sort of relatively high redshift LRGs. Redshifts about 0.4 to 0.7. And these are sort of the lower redshift LRGs. This is sort of focusing on the BAO feature. And this is remarkable because this is the last 10 years we have gone from barely detecting this feature to now being able to do relatively precise cosmological measurements with these things. And this is not sort of the end of the story with these surveys, where we're busy thinking about how we can keep analyzing these surveys and pull more information out. And so another final plug for sort of new results. This is work that I've been doing with a student of mine, sort of trying to map out what the expansion history of the universe looks like. These are simulations. This is not data. We're looking at the data as well. But this is sort of mapping out what the angular diameter distance is doing as a function of redshift from redshifts 0.2 to 0.7. That's sort of these are simulations, so the answer is very close to the mean value out here. And this is the same thing for the Hubble parameter. And we can sort of actually map out parametrically, of course, but sort of parametric with a sort of very broad possible choice of parameters, map out what the full distance redshift relation is. So we can actually translate the BOSS measurements into things that look like what do we know about where the distance redshift relation is doing. So this is sort of the motivation for having a meeting like this, which is the surveys currently have been incredibly successful. We built on these. We hope that the next generation of surveys are going to be just as successful as these. So how much information can we get out of them? BOSS. This is all BOSS. We can do this with BOSS. We haven't quite. These are simulated BOSS maps, but we're in the process of doing this with BOSS. Well, they're correlated measurements, but this is sort of the. Yes, the plots here have some degree of correlation between them. So, yeah. Right. Yeah. But then the piece here is really the early versions of these plots that you've seen were plots where you'll be certain sets of points on this figure. Always lead to discussions about where do you actually measure these things. What does it look like over that entire region and things like this? And now we basically can tell you this is what the expansion history of the universe looks like, and this is sort of that range of scale. And this is the sort of range of possibilities we have over that range. So here's a biased version. This is a figure that was prepared for the snowmass discussion 2 years ago now, of what the sort of scope of surveys looks like, of galaxy surveys looks like. All of these are sort of driven by dark energy, and this will become important in a second when we start talking about discussing how these survey designs run. And this sort of runs all the way out to 2027, 2029, starting off, and these are color-coded. Red surveys are spectroscopic surveys, blue are photometric surveys, and then things that are black are sort of some combination of spectroscopic and photometric surveys. So we have lots of these surveys that are going to happen between now and the next 15 years or so. So there's lots to do, and I think given that this figure shows both spectroscopic and photometric surveys, the first question that I want to sort of leave you with, is we've got sort of three ways in which we can think about doing these surveys. We can talk about doing imaging surveys, we can talk about doing spectroscopy, and then there are sort of more interesting new ideas that have come about, things like 21 centimeter intensity mapping, where you don't say, forget about the galaxies altogether, let's just do a CMB style experiment with the galaxies, and ask how well can we do out here. And so I think one question that I think will be an interesting one to try to get a handle on is, how much information do I actually get out of cross-correlating all of these surveys? Is there really new information that I can qualitatively get to either constrain models out here that I have different versions of maps of the same region? The standard answer here is, of course, always yes. But I think we have to sort of sharpen that answer from beyond, yes, I can just measure a cross-correlation. We can always measure that cross-correlation. But can I go from beyond that measurement to say, what sets of parameters do I actually get a handle on through that cross-correlation, as opposed to getting yet another measurement of the galaxy power spectrum on these scales? I think another question to ask, given the fact that we have LSST going to happen over 20,000 square degrees of the sky, and will be the deepest imaging survey that we will have for a very long time, I think a question to ask is, how much can we do with imaging surveys? If I can only get photometric redshifts, how far can I push those imaging surveys? And I think one question that I will ask here, and sort of jump to the next point, is we will have imaging and spectroscopy. We will have sparse spectroscopy overlapping with very, very deep imaging. How much information can I pull out if I use the higher densities of the imaging surveys with the sort of three-dimensional information that the spectroscopy gives me? So I have a skeleton that the spectroscopy lays down on the field, but now can I go after this and go and try to measure what use the the higher density imaging surveys to sort of get me a better estimate, a higher fidelity estimate of what the density field is. There's been some work, people started to play with this. There's work by Jens Jasch and Ben van Delt, who've tried to sort of do Bayesian reconstructions of what that density field looks like. Do those ideas actually, how well can one push those ideas? What is the sorts of what's the sorts of systematic levels? Can we do this at the level of precision that we care about doing? And then we sort of talk about intensity mapping. I think there's an interesting question here, which is, what is the relationship between intensity mapping and spectroscopy? I'm sure Kendrick will talk a lot about foreground removal. Are there games we can play where we sort of combine the fact that we've got intensity mapping and spectroscopy in the same region to sort of mitigate some of the issues with foreground removal? The fact that I've lost both sort of very large-scale modes and very small-scale modes in some of these questions, does that hurt me when I'm trying to go after systematic effects? Does it hurt me when I try to model what I'm actually trying to see? I think is a question that I don't know the answer, but I'll pose that as a question out here. Okay, so now we talk a little bit about survey design. So this is sort of the flowchart of how we've built all of these surveys. And the goal here is you've got to choose a couple of things. I got to choose the area and redshift extent of my survey. I've got to choose the number density of objects that I want to go after. I need to choose the tracer that I want to go after. And this is really, in some sense, when we've done these surveys, it's what objects can we get? And if we can get two objects, which one has the higher bias objects? And then what scales am I thinking about working with in the surveys? And this is normally a scale of about k of 0.1. We can play around with a factor of 2 out here, but it's no more than that out there. And so the usual calculation goes along this way. If I say what's the signal and what's the noise that I get, and I write down an effective volume for the survey, which involves this magic factor of NP out there. And the standard law is I want NP of 1. Once I've got an NP of 1, so I've got my number density matched to my expected clustering strength, I'm going to stop going deeper, and I'm just going to start going wider, because now volume is the key measurement out here, because my signal to noise in a pure signal to noise for most cosmological measurements will straight scale as volume. So statistics will scale as the volume. So I just want to get as much volume as I can in this game. So you try to do these very, very wide, very shallow surveys, which is what for a single right. So this is all within the case of single tracer versions, and I end up with these very wide, very shallow surveys. I think this is a question we should be asking: is this sufficient? And again, I think the question here is more than, if I want to get the highest signal-to-noise measurements of cosmology. So clearly, I want to get the most volume. I want to get the error bars as small as I can. But I also want to do this in the most robust way that I can. And so there's going to be a trade-off between what do I need to develop robustness in my measurements to what do I need to just get that volume. So how do I sort of piece those bits together to get sort of a coherent survey strategy over that case? So what considerations should we be thinking about for these surveys? Where should we? Is it overlapping of tracers? Is there high density regions? How much high density? What areas do we need? It's very easy to say, I'm going to do a systematics test. And this is a lesson we've learned from Boston and other surveys. It's very easy to say, we want to do a systematics test, so we want a region where we overlap blue galaxies and red galaxies. So we can go out and measure a BAO measurement in the blue galaxy region and the red galaxy region. The problem becomes very quickly that I've done most of my surveys in the red galaxy region. And so now I've gotten 1% very, very precise measurements out in the red galaxy region. The blue galaxy region is surveyed about 20% of that region. So my error bar out here is larger. So I'm kind of stuck in this case where I can say at the 5% level, they agree, because that's the measurements that I can make. I can make a 5% measurement in the overlapping regions. And at the 5% level, they agree. But I can't say anything about the 1% level. And really, I didn't care about the 5% level. I cared about the 1% level where I'm spending all my time doing the measurements out there. So it's very easy to say we will try to overlap and build these small degrees of overlaps in here. But it's very, very hard to actually get that to work, because you actually have to get that to work. You need to have the same level of accuracy in both your tracers. Otherwise, you're not talking about the same measurement. You're talking about one thing which is very, very precise and one thing which is not. I think a question that you can ask theoretically is, do we understand what's going on well enough that I can somehow predict that if I can measure things on small scales well enough, that I can say I understand these properties well enough that where I have high signal to noise even over a small region, that I can actually push that out to large scales. Because if I want to do this on large scales and get 0.1% measurements with 3 tracers, that's just not going to happen very soon. There was a question there. You hit exactly the same problem with the cross correlation. I can do these cross correlations, and now I get a cross correlation measurement where the signal to noise, the error bar is large, and large is a factor of 2 or 3 larger than what I care about. So you need a cross correlation where the cross correlation is as sensitive as the autocorrelation to actually do a meaningful comparison at the systematic levels that we're talking about doing. And that's always very, very challenging. If you sort of talk about the sort of large-scale the sort of simple tests you can do, yes, I can easily tell you at the 5% level, probably at the 2% level. But for these next generations of surveys, we're talking about 0.2, 0.3% level. So the cross correlation also has to be that accurate out there. And in lots of these cases, the signal to noise in the cross correlations, if I talk about simple cross correlations, isn't anywhere near as high as that. So that's the challenge. And that's generically the challenge with all of these measurements, which is why people keep building these large surveys that go out there. Yes. Absolutely. So I think that's an important, that's the way to think about how you frame this. I didn't have the answer to what you do here, but I think we need to be saying these are the measurements that I will do. Theory has to tell me, or theory has to tell the survey design, these are the measurements that you should be doing on small scales. This is the level of precision you need to measure them. This is how that precision translates into the precision on large scales, right? So you have to make all of those jumps before you can say you will gain the significance that you will get from those scales. Okay, so I'm going to stay away from showing you forecasts of surveys, because all these surveys do great in dark energy, so you can just believe that. I will show, partially because I'm biased out here, and this is a discussion about biased tracers, but I will show you a few slides on DESI, because I think, not because I think DESI is sort of the best survey that's going to do that, although we can have that discussion later, but because I think it's an archetypal survey which we can use to think about all of the other surveys out there. So here's what DESI looks like in case you haven't heard either me talk about it or someone else talk about it over the last few years. The idea here is to build a large spectrograph on the Kitt-Peak 4 meter with 5,000 fibers. So basically do Sloan a factor of 10 bigger out there. So this is the 4 meter telescope over a field of view which is about 3.2 square degrees. And the goal is to do 5,000 objects at a time. At the end of the survey, get about 25 million objects. By contrast, Sloan today, the BOSS survey, has about 1.5 million objects. So let me tell you a little bit about the surveys that go into DESI, and this has changed a bunch over the past year or so. So there's some new information here. The first one, so we're doing every tracer we can imagine getting with a 4 meter telescope. The standard tracers are the luminous red galaxies. You can get red galaxies out to a redshift of 1. We've done this with BOSS, so we're just going to keep doing this, pushing this out to slightly higher redshift, but really just plowing this region as deep as we can go with DESI out to redshift of 1. The next piece is our emission line galaxies, and we've already had some discussion about these. These are very, very different beasts from the red galaxies for a lot of reasons, and I'll touch upon some of those in the next couple of slides. And the goal here, this is where the volume comes in the survey. And the volume here is going out to a redshift of 1.7, but the sample selections are now, and the completenesses of the samples and things like that are very, very different from this. Quasars, we're trying to get quasars. This was largely driven by goals of measuring things like non-Gaussianity. Again, quasars, I think, they're not, in some sense, a complete. We'll get all of what we think are the quasars. What that actually means in terms of the halos that they propagate and how that selects things is an interesting question. We'll get the quasars out to a redshift between 1 and 3. Lyman alpha forest out, and I think Andre will talk about this, out from about 2.5 and greater. So, and then the other piece that I wanted to highlight here was this bright galaxy survey, which is a new idea here, which is basically do Sloan, replace the Sloan number here, which was 17.77, out to, Jeremy, you've got an updated version of those numbers. Right, good. So, basically do Sloan, higher redshift, deeper. But the goal here is a complete sample of objects, or as close to a complete sample of objects. And if you think about the success of Sloan, was, in some sense, it was a magnitude-limited sample, so you could play a lot of games that would become a lot harder with these color-selected samples. Here's what the redshift distribution looks like, and this is where I come back to these questions about overlapping regions. There's interesting overlap out here, and we'll talk a little bit about estimators. There are questions about, can I do clever estimators where I have overlapped regions to somehow cancel out sample variance? But I will sort of caution that the overlaps don't immediately give me the systematic control that I care about for the same reasons that I brought up earlier. It's just very hard to get the same volume. Juna. And we're partially selection. It's partially selection. The selection is just failing out past that point. No. In part because getting the imaging for the 14,000 square degrees is challenging enough. So we'll be glad when we get that. So there are overlaps, but I think we should discuss where those overlaps are and what we should be doing. Okay, so I want to talk a little bit about how we want to be thinking about analyzing these surveys, because I think, again, this is a question which I think theory can help inform things a lot. We can think about these measurements as being split into 2-point measurements and everything else, because the 2-point measurements are the ones that we've been sort of pushing the hardest up till now. And I think we want to be thinking whether it's possible to design estimators that are insensitive to nonlinearities, or at least suppress the nonlinear signals out by some large level out there. There's certainly been some work about this, and including people in this room trying to build estimators that suppress these small-scale contributions to these terms. There's a bunch of questions I think you can ask in these overlap regions, which is, how do I weight the galaxies? Can I use the fact that I've got 2 tracers in that region? can I use the fact that I can maybe get halo mass estimates for these objects to appropriately weight the objects to suppress things like shot noise in these cases? What do I need to make those measurements, and how well do I need to make, how well do I need to know things like the halo masses? Where are those halo masses going to come from? As you start going to higher point functions, I think this is still a very, very open question on what's the best things to be doing out here. We'll hear, I'm sure, a bunch of talks about sort of optimized estimates going after particular configurations. I know Chen Ting did a bunch of work, and Marcel Schmidtful has done work on this, trying to design optimized estimators that go after particular terms in the higher order functions as opposed to just measuring the full 3-point function. And then what's become very popular to think about is, can I actually forward model the entire problem? So can I start with an initial density field, and conceptually at least run an n-body simulation with galaxy formation in it, or some way of populating galaxies, look at what I get with the survey, do a likelihood measurement out there, and then just repeat over and over again. It sounds that it would never work. It's tremendous that people have been able to actually build tools to actually be able to do this in lots of cases, at least on large scales out there. I think there are two gains that one can get out of this, but I will leave you with some questions about ideas along these lines. I think if the question is, do I want to understand what's the evolutionary history of these galaxies, of the dark matter field that these galaxies live in? I think the fact that I can get these measurements to work right now gives me a good idea of, what's the sort of merger history that's going on out there? What's the sort of, how did the dark matter field in that region of where the galaxy is, how did that evolve from the initial conditions? What happened out there in particular for that object? So I can now ask object by object what's going on out there. So I think that's interesting in and of itself, if my question is galaxy formation and evolution. I think there's a question that I will ask you, which is, when it comes down to doing precision cosmology, I have to build in a model here that says, I know how to first do the dark matter evolution perfectly, and be able to do that fast enough. And that's always the challenge. So now I have to make approximations to doing the dark matter evolution. So I can't run the full n-body simulation. But then I have to have a prescription for putting down the galaxies. Now, if that prescription is not right, what has that done to my cosmology estimates that I've gotten? What does it do to my initial density field estimates out here? And the question that I want to sort of ask is, the other piece is, what happens to systematics in this case? So I have some observational systematic, and it's an observation. There are observational systematics that if I know the observational systematic perfectly, I can put that into this forward modeling and go all the way through. So let me assume there's a systematic that I don't know. This happens, really does happen with surveys, that there are systematics that we did not write down out there. In a case like this, where I'm running the systematic, when I'm sort of running from initial density field to final density field and looking for the systematics are not going to sort of nicely map from the final density field back to the initial density field in some clean way. The optimization algorithm is going to say, I've got to map this density field out here. And it's going to say, let me take these systematics and spread it out over all of the k modes that I've got. And so now I can put this systematic and put it around in a bunch of different k modes out here. And then the question becomes, how do I actually diagnose that I have a systematic error in the data versus something interesting going on in my survey? A lot of my systematics live in some nice space in the final density field, where I can imagine cutting the sample in lots of different ways. That becomes a lot harder if I'm running things back and forth. Now, this is not the only thing that I would do. So clearly, I can imagine diagnosing some of these things before I run these cases and imagine I've taken all of these systematics. But I think there's a word of warning, which is, I've taken an error which lives in some part of parameter space and now spread it out over my theory space in some funny way that the computer knows what it did, but you don't have any idea what you've done in that case. So that brings me to talking about observational systematics. And in some, we've been very, very lucky. Sloan and even Boss to that extent were very, very nice surveys to work with. There were relatively simple selections, if we selected red galaxies, we got most of the redshifts for those red galaxies. When I say most of the redshifts, I mean greater than 90% of those objects. We got redshifts for these things. And they were the objects that you thought they were. They were not some random thing floating around in your sample. And Sloan was even better. Sloan, just got everything out there. And even with those surveys like that, there were systematics we worried about. There were systematics in the target catalog. Star-galaxy separation was and still is a pain that we all deal with. Photometric calibration. Is the survey actually uniform across that entire region on the sky? As we start going to these next generations of surveys, things like the survey selection function will become significantly more complicated. It's not just the fact that the radial selection function, how in redshift do I select? As you start looking at these emission line galaxies, as I go past redshift 1.5, I'm working inside the OH forest in the atmosphere. So maybe that line hits an atmosphere line, a water line, and disappears, and maybe it doesn't. Maybe those water line strengths, how do those vary as a function of seeing condition of atmospheric conditions in time? So what does that selection function look like is going to get vastly more complicated. And this is true not just for things like, this is true for things on the ground, but there's similar issues that start happening in things in space as well. The angular selection functions are also getting complicated. These surveys I've tried to piece together. Sloan was a single camera observing the entire sky, the entire region. We're now piecing together different photometric systems. We're piecing together different surveys together to get these surveys, and you have to start worrying about them. But I think even worse is they're no longer separable. So one of the things we've enjoyed doing is we've been saying there are systematics that live in angular space, and there are systematics that live in radial space. I can just project out those modes. There's a small number of modes compared to the three-dimensional modes. If these start getting to be very complicated functions, projecting out knowing what modes to project out becomes very, very hard. In this case, I could just throw out all the angular modes, and I could throw out all the purely radial modes, and I'm done. I don't have to worry about thinking about this problem. If I have to actually know which modes I've messed up, and there's some complicated combination of angular and radial, I have to have some way of doing that. So then it comes to be, how do I go about doing those measurements? And that becomes a question about, do I have to forward model everything? That becomes hard, because forward modeling means it's very hard to sort of put something into a black box, have a result come out, and then hope that that's the right answer, and there was not a bug in the code that someone wrote that went through, or something that was just missed in that process. And then finally, these are all no longer high completeness samples. What have you actually selected when I pick emission line galaxies? A lot of the things that are in the target selection boxes will not have redshifts, because they will not actually have a bright enough emission line. They might not even have an emission line in those regions. What have you selected out here, I think becomes an interesting question, and how do we model what those are? I will say one word. Well, fiber collisions this is just one example of the kinds of things that just get worse. These were bad and slow. These were painful to deal with in Sloan. They just get worse with things like DESI or Euclid, with slitless spectroscopy, or with sort of movable fiber positioners. And again, I could do this at the 5% level. We're talking about doing this at the 0.1% level. Can I get these corrections? Or can I build estimators that immunize me to these effects out here? And then the final piece, because that's what I've been thinking about, is how do I actually think about, I've done the measurement. I now want to do the cosmology with this. And so how do I actually build my likelihood functions? Let's for a moment forget about the fact that the likelihood function may not be Gaussian. Let's just assume it's Gaussian. And the only problem that I have is I have to work out what the covariance matrix is. And the covariance matrix here is the complicated piece, because it's not just the covariance matrix of a 2-point function. It may be the covariance matrix of the 2, 3, and everything else that you're trying to fit out in this case. And the ways that we've done this up till now have been mostly brute force. I run lots of simulations, and I get those measurements. That clearly doesn't scale out to these next generations of surveys. I can't quite make that happen. So I think there's a real question here, which is, can we do better in those? I think theory here, in what cases can I actually calculate or have a good model for that covariance matrix? Can we actually do that? And then can we use what we know about the structure of the covariance matrix to help us in those cases out there? So I'll give you 2 examples, and I'll end. The first one is sort of doing this with modeling this. And so there's a lot of work that's happened recently, that's happened over the last month on the archive. Here's some work done by Ross O'Connell that should come out very soon, which is a sort of one-parameter model for the galaxy two-point correlation function, the covariance matrix for this. This is the precision matrix out here. These are the mocks from BOSS. This is the model fit. This is the model, the best fitting model, and here's the mock minus model for the covariance matrix. And the takeaway point is this is basically now 0 out there. So I can model what that precision matrix is doing relatively well with just a single one-parameter model. And one parameter I can actually hope to fit, or try to figure out ways in which I could try to measure it or understand it. The other piece that I want to highlight here is this is a very, very structured covariance precision matrix. It's very, it's very, very band diagonal out here. And so can we use ways to sort of use that structure in the precision matrix to go about doing this? So this is work that I've been doing with Martin White and a colleague. I'll just jump here, all the way here, with a colleague in statistics, Harry Zhu. And this is basically saying, let me use that structure in the precision matrix to reduce the number of simulations I need. If it's a structured precision matrix, I should be able to reduce the number of simulations. So here's just a mock example out here. This is the two-point correlation function, the monopole and the quadrupole, from a survey like BOSS. This is how the error in the precision matrix would fall off if I was just doing the standard trick, which is I'm going to run n simulations, and I'm going to invert a covariance matrix. And it starts to fall off, but you can see there's a relatively large error even at 2,000. It's falling all off at square root of n. So this is, square root of n is just the worst way to win anything in errors, because you just have to keep going down to very large numbers. But if I can use that structure, I can play games where I can start doing with reduce the error bar, and then start falling off much, much quicker out there. So in all of these points here are using the structure in the precision matrix to go after and estimate things directly. And I'll point out something interesting in this figure. This is a 200 by 200 covariance matrix. The precision matrix, if I do it by sample precision matrices, I can't do by, I need at least 200 objects, because I can't invert the covariance matrix to get this thing. If I'm using the structure in the precision matrix, though, I can actually do with fewer samples than the number of the dimension of the matrix out here, because the matrix itself is incredibly structured. So this is with 150 mocks. I've actually directly estimated what the 200 by 200 precision matrix is. And at least in this case, and I'm not saying this is generic, but at least in this case, we do about as well as you can do with 2,000 mocks out there. The takeaway here is not that this is the way we're going to solve all of these problems. It's really that I think these are problems that we're going to have to deal with when we do survey design, and we're going to analyze these surveys, where I think there's a lot to come in from thinking about this from a theoretical side. So I'll leave you with that. Thanks. This is just a correlation function. This is the full. I think we did 50 to 150 megaparsecs or something like that.
Right. Yeah. So as you push towards smaller scales, presumably
the structure will change. Right. There's an interesting question of why is the structure in the covariance matrix, the precision matrix, that structure, and we can talk about that. I would argue that that structure that you see, which is very, very banded out there, is relatively generic for all of these covariance matrices, even on small scales. Even on this is not using the fact. So this is I think just a mathematical curiosity about the covariance matrices we deal with, which is the covariance matrix itself is dying off as you go to large scale. So the difference between 2 points that are well separated in covariance matrix in point space there is sort of dying off. And you can now ask, what is the structure of the inverse of a matrix where the things are dying off the diagonal? And those things all generically tend to have very, 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 very sparse, very banded inverses. So there's a limiting case which is kind of fun, which is if the power law die-off basically gives you a tridiagonal inverse. You can show that's analytic. And so this is not quite a power law die-off, and it's not stationary. So it's a different die-off at every case. So it's a little more complicated. Yes.
that what structure that crystal makes. Because we know that the correlation function, you start with one that's close to a power law.
Yes.
Um,
So
even the selection effects tend to be local in physical space, and that has a certain certain structures.
yeah, so this argument, you can make that argument a little bit more precise. The argument I was just giving Neil, which is if I think of if I think of the power spectrum as basically looking at something like 1 on k squared, I can now roughly tell you what the k-space behavior of the covariance matrix is. Once I can do that, I can now, because I think of the covariance matrix as a convolution, I can basically start writing out the precision matrix as derivative series. And so I can think of the precision matrix as basically looking like a sequence of derivatives, basically k squared, k to the fourth, and higher order terms. So I can show you, let me show this. This is kind of fun to see. Here's the precision matrix. I'll show this movie. This is a slice through. This is just going to do a slice through the covariance matrix, and it'll show you the inverse of that covariance matrix, and show you that structure out here. And so this is the same structure. You'll just see this go by very quickly. Stop there. That sort of, is very banded. It's very tridiagonal, and it looks a lot like a derivative, second derivative. And then they're higher order terms. Hirsch. Yes. Well, so there are two pieces to this. This has got nothing to do with a model for Gaussian or non-Gaussian. This is a generic statement about covariance matrices. So I'll argue that there are generic properties of covariance matrices that go beyond cases where it's a two-point function where I agree with your argument out there. If I'm doing something which is a complicated statistic that I've calculated on the data, and I now need to compute a covariance matrix for that, which is things that we've talked about, people have talked about doing, then this is just using the structure of what I think the precision matrix structure is, and just utilizing that. I agree that you can sort of use for the cases where I can actually calculate things, I should actually calculate things and build a model in it. And so the case that I showed previously was doing that, was basically writing down the model in Fourier space and Fourier transforming it and asking what does it look like in configuration space. And there you can build sort of a one-parameter model directly. So there are two pieces here. One is a more generic statement, whereas when I can't calculate things, how do I do it? And then the second one is when I can calculate it, I agree with you. You calculate. Fabian. Yes. Yes. Yep. I don't know. I don't know the answer. I don't know whether it's easier to say I'm going to work in the I can keep my data. I'm not trying to pull the systematics out of the data and then try to use the fact that I'm still working in the final data space where the systematics actually live to make cuts there, than to do a forward modeling. I was sort of warning that the forward modeling is very seductive in that it sounds like clearly the right answer to do. And I sort of agree with it in that if you could pull it off, it is the right thing to do. It would be a wonderful thing to be able to do this. I think there are just challenges and the things you have to worry about for a real survey to pull that off and then claim that you've gotten something at 0.1%, which I think, there are devils in that detail, which you can keep saying that, they'll always make the argument that if I know the systematic, I can put it in, and that's absolutely true. It's the ones that I don't know that I will discover later that I. argue impossible, but even go so far as argue impossible.
Our particle physics colleagues who have not worked with astronomical data.
Yes.
You could also look at, as the way surveys come in, you could look at 10%. Right? You learn a lot from design techniques. All these surveys will have the factor that you would get 10% of those scores.
That's not guaranteed, by the way. I will sort of say, you can absolutely do a survey where you will not get 10% of the final data first, and that's a